Hey, you're probably wondering why black holes are so bright, even though they trap all light. Well, I'm here to answer that question, and probably pass up from a lack of oxygen to my brain, but here we go. The key idea is that this luminosity actually comes from the stuff falling in rather than the black hole itself. Many black holes are in binary systems, with the other object being a main sequence star or a red giant that has outgrown its Roche lobe, also known as the region of space with gravitational potential such that any object within that region is gravitationally bound to the star. The intersection between Roche lobes will be the L1 Lagrange point between the two objects, and that's where the gas will be funneled through. The key idea is that the gas doesn't just fall straight in, though. It has angular momentum because of its motion, and thus begins rotating around the object, forming what's known as an accretion disk. Once this disk forms, its motion is dominated by gravity. By doing a bit of differentiation into infinite slices, we can say that there's a bunch of rings in this disk, and each of these rings follows Kepler's laws. Thus, the closer you are to the center, the faster you move. So, if the inner rings move faster than the outer ones, then you have the shearing effect, and so when those inner rings move, they tug on the outer ones and form a method of angular momentum transfer for them to be able to move faster physically. The brightness of this disk comes from the fact that the materials themselves are basically just an enormous soup of hot ions bouncing around rapidly, but there are a few more things that I think are worth talking about. The shearing and tugging effects mentioned previously cause a lot of friction and heat in addition to creating a lot of viscosity. However, doing the math shows that any matter created from this method would result in a gas packet on the outermost ring taking longer than the lifetime of the universe to fall in. So what gives? There's actually a bunch of other things at play, such as something called the magnetorotational instability, the MRI, and various other turbulence effects within the gases, which cause the fluid like this to have an effective viscosity that allows the infall of matter. In fact, if you try to model this from first principles, the disk is governed by the full Navier-Stokes equations, basically a set of nonlinear partial differential equations describing fluid flow. But if you look closely, the thing we actually care about is this viscous term. This is what controls how angular momentum gets transported. So instead of solving the full equations, which is basically impossible analytically, we replace all that messy turbulence with an effective viscosity. And that leads to the alpha prescription, where the viscosity is modeled as alpha times the sound speed times the disk height, which turns this unsolvable problem into something we can actually work with. Also keep in mind that this only works with thin disks, where the height of the disk is much, much smaller than the radius. Okay, wrapping up a bit, there's actually a limit to how bright these disks can get. Eventually they heat up fast, producing higher and higher frequency radiation until you reach X-ray levels. Inward gravitational forces get met with outer radiative pressure, which eventually matches gravity in equilibrium. The maximum possible luminosity is defined by this Eddington limit, or Eddington luminosity, determined by this equation, which was derived by setting Newton's gravitation equal to the radiative pressure equation. Also, accretion as an energy source is incredibly efficient. Using mass energy equivalents, even a small amount of mass can release huge energy. For reference, nuclear fusion converts about 0.7% of mass into energy, but accretion can reach upwards of 40% depending on the compact object, resulting in this ridiculous brightness. Okay, so this truncates at the spin-dependent ISCO, so pure black holes that matter orbit closer and push efficiencies towards 40%. As this radiative flow is fully relativistic, so you get gravitational redshift, Doppler beaming, and strong field lensing, making the disk highly asymmetric. The spectrum is a multi-temperature black body with temperature scaling like r to the minus 3/4 and luminosity proportional to mass accretion rate. Inner regions become radiation pressure dominated, triggering thermal and viscous instabilities and possible limit cycles. Angular momentum transport isn't molecular viscosity, it's magnetohydrodynamic turbulence with the Maxwell stresses dominated by MRI. Magnetic fields thread the disk in black hole, launching relativistic jets and extracting rotational energy through frame dragging in the Blandford Zionic process. You also get corona formation above the disk, producing inverse complex scattering that boosts photons into hard X-rays. Spectral lines like iron alpha get brought in and skewed by relativistic effects, letting us actually measure black hole spin. And if you really try to describe this first principles, you end up solving a coupled system of non-partial differential equations, basically the relativistic Navier-Stokes equations combined with Maxwell's equations of curved spacetime, because they do change because of the fact that you can't assume globally inertial reference frames. And if you want to model any of this, you need full GRMHD because the stress energy tensor radiation transfer magnetic fields and curved spacetime are all non-linearly coupled. And all of that because of gravity.